All right, let's what will the format for quiz 2 be? The quizzes are on I'm going to talk about the quizzes later, but the quizzes have been on Canvas since before the course started, and you're welcome to do those anytime before the deadline. Just hop onto Canvas and complete them.
Did you intend to have them be as many attempts as possible?
Yes.
Okay.
Yeah, they're not really intended to, like, weed students out of the program or something like that. They're intended to let you self-assess your understanding, and you can keep working on it until you get it. But I want you to do the quizzes on your own. Don't Google the answers or something. They're especially the GDB quiz, which is intended to be kind of a hands-on lab. But mostly they're just kind of touch points throughout the course to assess your understanding. And the deadlines, I just kind of set them up to be far enough in the future that hopefully we've gotten through everything before, long before the deadline. So yeah, I think later on today we'll actually run through the quizzes and just kind of look at the questions and make sure everybody knows what they're being asked, and particularly the GDB quiz, which is kind of a lab. I wanna run through that and make sure people can get started on that one. Any questions on PA2? I've only seen like 2 of these submitted. But any major difficulties or concerns? All right, well, let's finish up talking about hashes, and then I want to talk a little bit more about lists, linked lists, and some other versions of linked lists, and then we'll go over the quizzes. What was your solution for keeping track of a tail pointer? I decided to use the Q data variable using double casting, but it seems very precarious. That's not a bad solution. It's not the one I had in mind. You can get away with that, though, because the way that things are packed on this version of Linux, there's always 4 bytes between the data and the next node pointer, so you can capitalize on that space. But there is a solution that should not depend on that sort of good fortune, which I can talk about next week after the assignment's turned in. But that's a pretty good solution you came up with, actually. So let's recall our setup for a hash table. At its heart, it's just a plain old array. It's an array of, if we're probing, it's an array of structures where, we have a key and a data pair and an in-use flag and a deleted flag, and we went through some rather complex pseudocode to see how to manage collisions by reprobing and using the deleted flag and so on to know if we have to reprobe when we search and all that sort of business. So there's a totally different approach to doing this, which is called chaining. And chaining is a fair bit easier to implement. It's the approach that you'll use for PA3, which I'm going to talk about on Monday, by the way, not today. I'll let everyone get through PA2 first. But you're going to use chaining instead of probing, so it's a little bit easier. And the setup starts the same. you have a key, and you run it through some hash function h, and it gives you an index, an integer, in this case from 0 to n minus 1. And that means, hey, this is where we should store the data associated with that key. So when we're using chaining, instead of storing the data directly in this array, what we have is a series of sentinel nodes pointing to linked lists. And when we initialize the hash, each sentinel would be, set up to have its next node equal to null, or whatever we're doing to indicate that this is pointing to an empty linked list. And then when you want to store something associated with a key, run the key through the hash function, find the index, that gives you a sentinel node, add your new data to the linked list that sentinel is referring to. And now it's just a linked list issue, right? So where do you add? Well, we don't need to add in order, so we'll probably just add in the beginning. So it'll be like, our push function from PA2. When you want to search, we'll start from the sentinel and we'll just follow from node to node until we find the data key pair you're looking for, or we run out of nodes. And if you want to delete, same thing. We start from the sentinel, follow the nodes till you find the key that you're asked to delete, and then delete that in the usual way, free the memory, and you're done. So it's like having a bunch of linked lists. Now if we just use one linked list to store all our data, that's an order n situation. A million pieces of data, a million operations theoretically you have to do to find something or discover that something is not in your linked list. What we're really doing here is making, say 1,000 linked lists. And if you only have 500 pieces of data, it's possible that each list is either empty or contains exactly one element. And when you want to retrieve, data associated with a key, you hash that key, you find an index, you look at the sentinel node. If that list is empty, your data is not in there. But it may be, if it's not empty, it's pointing to a node that contains your data key pair. And so this can still be order 1, even though linked lists are kind of inherently order n, as long as the lists don't get too long. Now, if there are 1 or 2 nodes per list, I don't care if it takes you 2 operations instead of 1, it's still order 1. But if the lists keep growing, and when you double the amount of data, each list doubles in length, that's an order n performance, and that's not so good. But as long as we keep the number of collisions relatively low, this will stay pretty close to an order 1. So the pseudocode for something like this is pretty straightforward. Assuming you have a linked list package, which you do, because you've written a linked list package in PA1, you've modified it and used it in PA2, and with maybe a couple of other modifications, it'll be perfect to use for PA3. So what do some of our functions look like? So this approach is called chaining. So what's the pseudocode look like? Let's say we want to init. So you want to create an empty hash table. Well, if we stick with the structure names and such from PA1, this would be an array where each entry is a pointer to a struct my node. So we want an array of these things, an array of struct my nodes. How do we make an array of something? Declare a pointer to it. So hash would technically be a struct mynode star star. But if you don't like that, right, make a type def. Right, let's make a new type of a variable called a sentinel, and let's just type def a sentinel to be a struct mynode star. And this isn't doing anything for us that we can't do without type defs, but sometimes it makes things less confusing. So I'm defining a sentinel to be a struct mynode star, and now I'm going to declare my array to just be an array of sentinels. Or I could have done, sentinel hash bracket 1000. This is a fixed size array. This is setting up an array without it actually referring to any location in memory. And so if I'm going to declare it to be a pointer to a sentinel, I need to do a malloc 1000 times size of sentinel. Or if I don't type def, 1000 times size of struct mynode star, 1000 pointers. And this is a good thing to ponder, and it's really good fodder for exam questions, by the way, because it really forces you to kind of like break down what arrays are, what pointers are, what sentinels are. Sentinels are pointers. A sentinel node is the address of, when we talk about a sentinel node, it's actually the address of a block in memory containing, 1, 2, 3, 4, 5, 6, 7, and another pointer. So all of these things should be pointers. What should they point to? They should point to a node. Right, so a sentinel is actually the address of a mynode. An array of blah is a pointer to blah. It's actually a pointer to the blah that is the first element of the array. So when I say sentinel is a pointer to a struct mynode, we can think of this as an array of mynodes, but we don't. We think of it as a pointer to the first node of a list. But when we think of hash as being a pointer to a sentinel, we're thinking of hash as being an array of sentinels, or an array of struct mynodes, or an array of pointers, each one pointing to another node that leads the beginning of another linked list. But we do something, right? And then we can just loop. Well, hash bracket I is going to be a sentinel node, so we could just, if this is our hash init function, we could just call our linked list init, hash bracket I equals init. So we call our linked list initialization function. What does that do? That allocates a block of memory for a node. It sets the data to a magic number. It sets the next and all. It returns the address of that block. So this assignment statement says, hash bracket 0 equals the address of that first block that we just allocated. And then when I equals 1, hash bracket 1 will be what we get when we call init a second time. When we call init a second time, it'll allocate a second block, return that address. This will be the address of that second block. And when we're done with this loop, what we have are 1,000 pointers to 1,000 different sentinel nodes, each acting like the beginning of one of 1,000 different linked lists.
And this is where that linear hash comes in, where you get to the member by using the hash algorithm as opposed to looping through the whole list just to find 800, for example.
Yep, exactly. So this is something that we're gonna dig into in PA3. This idea of building a data structure on top of another data structure. And we're actually building it on top of a third data structure if we think of an array as a very kind of, simple example of a data structure. And the whole part of the power of creating something like a linked list or a data structure is that it's a way to organize information, but that information can be pretty much anything that you want. And so in this case, when we look at our linked lists, they're going to be comprised of more complex nodes. We're going to have a sentinel, and that's going to point to our first node, and that's going to point to our second node, and so on. But our nodes are going to be triples. There's going to be a key, which is probably a string, and there's going to be a piece of data, which is probably a string, and then there's going to be a pointer to the next node. And when we're searching, when we're trying to delete and we're looking for something, we're really going to, key this off of the key. The data is kind of a payload that just comes along. So if we want to delete, a license plate ABC123, we're going to start at the sentinel, move from node to node using the next node pointer. And as we move through, we'll see if the key matches what we're trying to delete. We're not really going to do anything with the data. When we search for a license plate, we're going to do the same thing. Start from the sentinel, follow the pointers from node to node, and compare the key to see if it's the key that we're looking for. When we find that key, then we take the data and we say, hey, here's the data that goes with it. But this payload piece of our node can be anything we want. It could be, a simple string that contains a name associated with a license plate. It could be, a structure containing a first name and a last name and a student ID number. It could be another linked list. It could be a hash table. It could be an executable program. It could be a WAV file containing music. So we're going to have a more complex node structure. But if we understand our linked list from PA1 and we change what the definition of a struct myNode is to simply add another field, none of our code really changes. So we're moving to a more and more modular world. Alright, so what do some of these functions look like? Well, we're not going to go into a lot of detail on these because, frankly, they are all pretty much the same business. So let's say we want to put key, comma, data. And let's just suppose that, we're insisting that the key is not already found in our hash table. We're putting in a new piece of data. So what do? We use our hash function, and our hash function doesn't take a probe number now. We're not probing. We're just, here's a key, tell me where that data should be stored in the hash table. So we get back an index to this array, something between 0 and n-1. And so now, if I want a temporary variable, I can say, sentinel equals hash bracket location. So I make a copy of, the address at that location in our table, and I save that in this local variable sentinel. This is a sentinel node of a list that we should put this key data pair into. And so if I have an add function, I can just call my add function, give it the sentinel. That's the first argument for the function that you wrote in PA1. And then there's two pieces of data to store, a key and a data. And this is, your code from PA1. Start from this node, move to the next one, loop until it's empty, and so on. But since we don't care about inserting things in order, right, we can just add right in the beginning of the list. So do what you're doing with your simplified add function when you implement push for PA2. And the fact that this sentinel came out of a hash table is irrelevant to the add function. Right, this is your linked list add function. All it wants is a sentinel node and the data that should be added. And you know, if we want to allow the user to be a little reckless, we could say something like, you know, if search sentinel comma key, then delete sentinel comma key. So before we try to add, we'll search the linked list and see if the key is already stored in there. And if it is, then we'll just go ahead and use the delete function to delete that. And then we'll go ahead and we'll use our add function. And then how do we fetch? So find the index for the sentinel node. And I don't need to, you know, put this in a separate variable. I could just put hash bracket loc inside here, and here, and here. But I'm just breaking it out into more variables. So, you know, make a copy of the sentinel node. That's what sent is. And we want to, you know, retrieve that piece of information. Well, you know, make something like... So we'd need a new linked list function, because our old linked lists, the thing that we were searching for, was the only thing that was stored in the node. If we said search for a 20, it meant is there a node that has a data value of 20. But since we have this more complex structure where we have, you know, two pieces of data, we don't want to just say is there a node with this value of a key, but if there is, what's the data value? And that's, you know, one extra line in your search function, which is when you get to the spot where you would return 1, instead of returning 1, you know, return the data in that node. So we'll make a get function, which is a modified search that returns the data associated with a key data pair. And then our hash fetch function just returns that data. And our delete does the same thing. Location equals this, sentinel equals this, and then call your list linked delete function to delete that node from your list. So really, other than, you know, having a hash function and making an array to hold a bunch of sentinels, this is just linked list code. But tying it all together into working code is going to be, you know, the challenge of PA3, plus the main program, plus some other details. So pseudocode for chaining in a hash table, not all that exciting, but pretty powerful.
In PA3, you're definitely going to expect us to use an array to tie them all together.
Let's see. Can you think of other options?
I suppose you could have a fourth member in the struct that points downwards, like in that picture.
Like what picture?
The current picture right there with the hash. 0 to n-1.
Okay. So to get the order of efficiency, we need a way to go from a key directly to the linked list in question. And so, for example, we could store, you know, these in a linked list instead of an array, but if we hashed a key and it told us, you know, use list 37, we'd want to be able to get to that list without having to start up here and move 37 spots from the top.
Oh, yes, yes.
All right, so that's what's making it order 1, because accessing an array is fundamentally order 1. But it's because of its properties that make it order 1 that it's so painful to insert or delete into or from an array. So this is kind of like some sort of weird hybrid between arrays and linked lists almost. All right. Other questions, thoughts on this? All right, so let's forget hashes for a few days. And let's go back to linked lists. And I want to just mention a few other versions or flavors of linked lists that we'll encounter sometimes. And so, you know, we know the basic list setup. So there's our favorite list containing a 10, 20, 30. And we want to insert a 25. We want to keep things in order. Let's see, does anyone remember if we went over linked list implementation for stacks? I'm pretty sure we did. Implementing a linked list with a stack is basically just doing all your business right by the Sentinel node. So when you want to push a new node n, make a new node, have the Sentinel point to it. So a simplified version of add that always adds right after the Sentinel. And then when you want to pop, just delete the node the Sentinel is pointing to and return its value. So a much simplified version of delete. We don't have to search for anything. Take whatever node the Sentinel is pointing to. That's the value we're going to return. Have the Sentinel point where this node is pointing, in this case, right here. Free this from memory and return the value that you saw in there. And it's even more straightforward than implementing queues. Because queues, you have to do something at one end, something at the other end. Stacks, you just do everything right there in the beginning. No, that's definitely topical, not an interruption at all. Alright, so inserting a 25, and the challenge here was, you know, where do we insert it? And when we're looking at this node 20, we have no way of knowing that this node 25 should come right after this. Because, you know, the next node might be 21. The only way we know that the 25 should come after this node is when we've gone to the next node. And so if we come out here, and we're looking at node 30, and 30 is bigger than 25, now we can say, we should insert after the previous node. Well, we cannot insert after the previous node unless we have a reference to that previous node. So this is why we have this whole business in PA1 of a previous current pair. 2 pointers that as we move through the list, we keep these things close to each other. We're looking at a current node, we're remembering the node that came right before it. We want to insert after the 20, we move those up. Here's the current node, here's the previous node. Now we find, we want to insert after the previous node. Well, we've still got a variable that's pointing to the previous node. And so now putting our new node in is pretty straightforward, right? Previous next equals new, new next equals current. And you're done. But to make that work, we needed to know the prior node once we got here. So one thing we can do to simplify this is make a doubly linked list. And so here's a 10 and a 20 and a 30. But we're going to have a pair of pointers in each node. And it's going to look something like this. Here's our data. Here's a pointer to the next node. here's a pointer to the previous node. And so the 10 would point to the 20 would point to the 30, and the 30 will point somewhere, and something's pointing to a 10. But the 30's previous value will point back to the 20, and the 20's previous node will point back to the 10, and the 10 previous will point back here, and something over here will point back to the 30. And so it's kind of like we have two linked lists in one. And so now if we want to insert a 25, we don't have to keep track of the previous node. We check 10, nope, check 20, nope, check 30, yes. Alright, this is our current node. We want to insert after the previous node. Well, we can find the previous node. It's just current arrow previous. That gives us a pointer to this node. So let's see what this looks like. So 20 is pointing up here. 30 is pointing backwards to 20. And we're putting a new node 25 in between. So we're not going to do anything with 30's next. That's going to stay unchanged. And 20's previous is going to stay unchanged. But we got to squeeze a new node into here. So here's our 25. And I'm going to call this node current. So we got to do four things. We got to change this to point to 25. We got to have 25 point to 30. We've got to have 30 point backwards to 25 and have 25 point backwards to 20. And in some cases, the order in which we do these things is important. So 25 is the new node. I'm going to set this node up first. And let me call this new. So I'm going to set up 25's pointers first. I'm going to say new arrow next equals current. So that's going to put up this pointer. That makes 25 point to a 30. And I'm going to say new arrow previous equals current arrow previous. Well, current arrow previous is the 20, so this is going to make new also point to the 20. And now I'm going to adjust the previous and current nodes so that they refer correctly to 25. So I'm going to say current previous next equals new. So what does this alphabet soup mean? Current is this node right here. Current arrow previous is the previous pointer. That's referring to the 20. So current arrow previous is this node. Current arrow previous arrow next is this node's next field. That's this block right here. I'm going to set that equal to new. So this is no longer going to point up there. It's going to point down here to new. And then current previous should now point to new. So instead of current previous pointing to the 20, it's going to point to the 25. Alright, did we do this correctly? So let's follow it in both directions. Once we get to node 20, if we follow the next pointers, 20 points to 25, 25 points to 30. That's good. If we follow the back pointers from 30, the previous points to 25, the previous points to 20. So this is a classic case where you draw a picture, you figure out what you want the picture to change from into, and you write code to correspond to that. But it can be tricky, and in particular these two instructions right here, if I do those in a different order, this doesn't work. Right, if I change current previous first, and then I change current previous next, I end up changing this thing's next field instead of this thing's next field. And this can get really confusing, especially when you get to more complex structures. So one trick that you can always use is use temporary variables. And I strongly recommend this. So instead of doing all of this stuff, let's just say, you know, previous equals current previous. So I'm basically giving a name to this node. And now how do I insert new in between them? Well, previous next equals new. New previous equals previous. New next equals current. Current previous equals new. And it saves me from, you know, having to come here and go back there and go over here and write a statement like this and worry if current previous still means what it is supposed to mean and so on, right? You can make as many local variables as you like. And I'm not allocating memory if I, you know, declare a struct mynode star previous equal current arrow previous. That's just a address. It's an 8-byte pointer that I'm setting equal to the value of whatever this is pointing to. So I'm setting it equal to this node's address. I'm not allocating memory. I don't have to free it. I don't have to worry about memory leaks, right? It's just a temporary pointer. But now I've got the advantage of this has a name, this has a name, this has a name. And so if I want to refer to this thing's previous field, it's just previous previous. If I want to refer to this thing's previous field, it's just current previous. If I want this thing's next field, it's just previous arrow next. And when we get into binary trees and more advanced binary tree code and balancing trees, we're going to end up doing a lot of really bizarre operations where we're going to start from one node and we're going to go up 2 levels and then come down to a child and all this stuff. And if you try to do this, you know, like this, you're going to end up with big long chains of logic that can conflict with one another. Use temporary variables. Give everything a name. And it just makes life a little easier. Alright, so that's one variation on a linked list. Another variation, and we can do this, you know, with singular lists or doubly linked lists, is at the end of a list, instead of pointing to null, we can point back to the beginning. And this can be useful sometimes if our data is of a nature where sometimes we want to just keep moving through our list until something happens or something is detected and we want to stop there. And then at some point we want to come back and continue from where we stopped. And so this would let us, simply avoid the question of if our next node is null, let's go back to the first node, right? And we could perhaps, just keep a single variable that refers to our current location in the list, and we just, current equals current arrow next, and we just do that to go through the list. Now there's, some details to keep track of here. For example, if you're searching for something in a circular list and it's not in the list, potentially you're going to search forever, right? You need some way of knowing when you've checked every location in the list. Otherwise, if you just keep following from node to node, you're going to run in a circle forever. So our logic's going to change. Our while loops where we say, while current is not null, those aren't going to make sense. But if we have a sentinel node, we could say while we haven't gone back to the sentinel node, or we could remember where we start, and we could say while we're not back at that node, and so on and so forth. So yeah, there's hazards like that we need to keep in mind. And sometimes we can make a linked list that does not have a sentinel node. And so, in a circular list, we may not want a sentinel node, because the sentinel node doesn't actually have data. It's really just a pointer to the beginning of the list. But if we're going to do something circular like this, that may be a case where we don't want a sentinel node. And we don't need sentinel nodes to make linked lists. They're purely a convenience. I could have, my list, which is a pointer to a struct my node, refer to the actual first data node. And if my list is empty, I could represent that by having list be null. But in C in particular, this complicates our code, because null is different from a structure that has a field that's set equal to null. And when we talk about binary trees, which are coming up either today or next week, we'll actually start with the idea of a list that does not have a sentinel node. And we won't have sentinel nodes for binary trees. And the main reason for that is because of some programming tricks we're going to use to write tree code. We're going to use something called recursion. And recursion doesn't work well with sentinel nodes, but it works beautifully without. The other thing I want to mention is that, our first linked lists, we had integers. And for PA3, our linked list will have a pair of strings, a key data pair where we're going to have a license plate and a name. But in general, we can put any kind of data we want into our linked lists. They don't have to be integers, they don't have to be strings, they could be linked lists. It could be that each of these is a sentinel node to another linked list. And you could have a list of lists, and people do this. And if you have, a good linked list package, meaning that it has this firewall between implementation and user interface, this is not a problem, right? And we're going to see this in PA3 when we have our array of sentinel nodes, right? We should not have to worry about, next nodes and nulls and sentinels and 1, 2, 3, 4, 5, 6, 7 and all this stuff, because all of our interaction with the list is going to be through 4 or 5 or 6 functions that you've written that describe your whole interface. And same thing here. If this data in this node happens to be a linked list, we can just use that as the first argument to our linked list functions. And when we say let's add something to this list down here, well, if we use this piece of data as the Sentinel node's address, right, the add function doesn't care. It doesn't get tangled up thinking, oh wait, but this is actually, you know, a node in another linked list, etc. It has no notion of that. It just gets the Sentinel node, adds to that list. And this is where the power of you know, encapsulating all of this behavior in a set of functions really kind of kicks in. And this is our springboard to Java and object-oriented programming in general in Spring. Alright, so there's some previews of coming attractions there. Any questions, comments about that? Alright, let's do a short break, and then when we come back I want to run through the quizzes in Canvas and just kind of touch base on those, particularly the GDB quiz. And then after that, we're going to start talking about a new type of data structure. So let's take a 5-minute break, and we'll come back at 5 minutes. Alright, I'll see you there. Okay, yeah, I was thinking about that.
Yeah, because then I'll jump for tomorrow.
Yeah.
So I'm just waiting for a call back from him. He's out doing tests already this morning.
Are these clean?
No, that's all ready.
Alright.
There should be cornbread by noon.
Cornbread?
Yeah. That's the plan anyway.
Yeah.
Yep.
Thanks.
I'll let you know.
Alright, we're back. So let's eyeball the quizzes. So quiz 2 is due on Friday. And so this is some conceptual questions about arrays and pointers to arrays and pointers to variables and so on. So if you declare integer x bracket 32, how does the compiler treat the symbol x? So is the thing pointed to by x bracket 0, the address of x bracket 0, the value, or the length of the array? And you can if you're not positive of this, right, you can write some code, declare integer x bracket 32, and then, you know, maybe try printing its value. Print the value of x. And you'll get complaints from the compiler, but it should still compile. And take these, you know, to some degree as sort of lab exercises. Don't just, you know, try to find the answer from your notes, or, you know, online or something like that, but really try to think about like what's going on in these questions, right? What does x mean to the compiler? If you were to say print x, what value will it print? If you were to say x equals x plus 1, what would happen? What would happen if you tried to access element x bracket 0? Right? So mess around with this stuff. What's the proper interpretation of y equals star x, assuming we said integer star x, integer y? So this is pointer dereferencing, right? We do this stuff a lot, and we'll do it more and more. So what does this actually mean? And there's some options here. Here's a question on structures. So structure called new that holds two integers. Variable is a variable of type structure new, and we want to set the x field equal to 0. So this is a syntax question, right? We have rules for writing C statements, and there's rules for how we interact with the fields of a structure. So structure is, you know, a keyword. This is defining a structure named new that has two what we call fields. So the pieces of a structure, those are what the fields are. So there's a field named x that's an integer, a field named y that's an integer. And typically we want to do things with those fields. We want to interact with the integer that we call, you know, the x field of this structure. So how would we set the x field of something called variable, which is a new struct? How would we set that to 0? And then here's the question on that arrow business, right? So, and this again is purely syntax. There's nothing in here that tells you, you know, what the answer is. This you have to know from your notes and from your code. But this arrow notation is a shorthand for something. So if you don't remember what it is, go back and look that up. And then which of the following will likely cause a seg fault? And these, you know, are four statements that all look pretty much the same, but there's differences. So really think about this, and this is a chance to play computer, right? Pretend you're a computer, and you're given these statements. Get a piece of paper, that's your memory, and what do? When you see integer x, you draw a little box and you label it x. And that box is big enough to hold an integer. And it has nothing in particular in it right now. When you say integer y, you draw another box and you label it y. And that's big enough to hold an integer and has nothing in particular in it. And when you say x equals 5, you take the value of this, which is a 5, and you write that into the box labeled x. Right? And this sounds rudimentary, but this is what the computer does. And you know, the individual statements of a C program are not terribly more complex than this if you break it down. It's mostly just moving stuff around and doing arithmetic and comparing things. And so if you can dutifully follow what your code is telling the computer to do, then you can analyze exactly what the computer is going to do when it runs your program. And if the computer's not doing the right thing, you can replicate that error on paper. And it lets you see exactly where the error occurs because, you know, as you're running through your program on paper, you get to a point where I should be equal to this, but instead it's equal to that. And you know, hey, my program just did something wrong. Why did it do something wrong? Well, I said this, and everything was right up to that point, but this did something different from what I thought. And there's a problem in that statement, right? So this is how you debug, right? If you don't have GDB running. Alright, so that's the first quiz. I'll see how I did on that. I think I got a 0.
I would like to mention one thing.
Mm-hmm.
Say that I started one quiz, then I came back to like 2 days later or something, and it said that my elapsed time was like 5,000 and something minutes.
Mm-hmm. Yeah, that'll happen. That's okay. There's no time limit on these, so if you start it and come back, you know, a week later, you'll have a long record time for doing the quiz, but I don't pay attention to the time, so that's totally okay. Alright, let's go through the GDB quiz and let's work through some of these together. So there's a file, an executable program under /tmp called G1. And you should run it using the debugger, right? So let's do this. So I'll hop in here, and if I just run /temp/G1, it's not very exciting. But if I gdb/temp/G1, I can run through my code, you know, a statement at a time. And maybe stuff will happen. Alright, so,
Really quick, Nick.
yeah.
Do you have to compile it with the -G before using GDB on it?
Well, what would you compile?
The temp file.
That temp file is an executable file.
Oh, okay.
It's not C code, so I've already compiled it, and yes, I compiled it with the -G so that you could do this. So yeah, the actual answer would be yes, but you don't have to compile it, I did. So start the debugger using the start command, so say start. And it's ready to start executing. So temporary breakpoint 1 at main line 19. But it can't show you line 19 of the file because you don't have the access to the source code. That's intentional. And if I try to list it, right, it's not going to show me any of my code. That's intentional. I don't want you to see the code. What I want you to do is step the program and analyze it using various GDB commands and then answer some questions about it. Start the quiz, wait 68 years and 1 second, and see if it rolls over. That is a good way to see what size the server is. I like that. Alright, so let's preview the quiz. Answer should be entered in hex unless told otherwise, and they should be lowercase letters, so like 0x, and suppress the leading 0. So, because Canvas quizzes are kind of unforgiving about format. So, question 1, start the debugger, set a watch point on I, and continue until the value of I changes. Continue repeatedly until I is equal to 5. What's the value of x at this point? Okay, so what's a watch point? We can set breakpoints, which say, hey, if you get to this line, stop executing. We can also set watch points, and we set watch points on variables, and they say if this variable changes value, stop what you're doing. So I can print I, it's got a random value to it right now. I can say watch I, and now the debugger is going to keep an eye on this variable, no pun intended, And if it ever changes value, it will stop what it's doing and come back to me and say, hey, this variable changed. Alright, so it says continue until the value of I changes. How do you continue? Just continue, or CONT, or just C. And it says hardware watch point to I. Old value equals 32767, new value equals 0. And it's at line 19 in G1.C. And this is, I believe, the program counter, so this is where the instructions are that it's executing in memory. And I is equal to 1. And if I print the value of I, or 0, if I print the value of I, it's 0. If I say continue, it'll run some more, and when it gets down to line 22, I changed from 0 to 1. And if I print the value of I, it's 1. So question 1, you keep doing this until I is equal to 5, and then print the value of x. How do you print the value of x? Just px. So you can get your hands dirty with that. How many bytes are allocated for the struct mystruct? Answer in decimal. Let's rephrase that. What is the size of the structure mystruct? That's a hint. And remember, GDB lets you do all sorts of things. Like, for example, I could say print size of an int, and it'll tell me an integer is 4. I can say print the size of a double, and it'll tell me a double is 8. I can say print the size of, I don't know if it'll let me do this. Print the size of an integer pointer, and it'll tell me it's 8. I can print the size of a character, and it's 1. I can print the size of a pointer to a character, and it's 8.
And its size is printed in bytes.
Yeah, that's a decimal number of bytes.
Okay. But the number printed in GDB is in bytes. Yes.
So this number is the result of this print command. Ignore these numbers on the left. So size of a character pointer is 8 bytes. Size of a character is 1 byte.
Size of a character in bytes. Yes.
Yes.
Okay.
Alright, so you can do this for structures. You can find the size of a struct mystruct. What's the starting address of the array named data? Well, we have a variable named data, presumably, and this is what its contents are. Just like we have a variable named I, and that's its value. If you want to know the address of a variable, I could find where I is stored in memory by printing ampersand I. So ampersand tells us the address of something. And so you can do the same thing to find out where data starts. And then figure out the address of data bracket 0. Figure out the address of data bracket 1. And what you're doing here is you're building a memory map. You're making a picture, perhaps on paper, of how things are organized in the memory of the machine while this program is executing. And we have this variable data, and it's an array. And it's got element 0 at the beginning of the array, followed by element 1, followed by elements 2, 3, 4, 5, 6, 7, 8, and 9. And if we look at the addresses of each of these, we can start to draw some conclusions about where this stuff is being stored. PA3 will come out on next week, probably on Monday. Alright, so using your information about where the data array begins and where the successive elements are stored, cobble together a formula for finding the address of data bracket I. and it will be one of these that will match.
What's the command for printing an address of something again? Did you
Just put an ampersand in front of the variable. And it's the same syntax as in C programs. If I want to find the address of a variable, I can say ampersand variable name. So I could store that in a pointer or pass it to scanf or things like that. So GDB is very C-like in its syntax. Alright, here's a typo for you. But the mystruct structure contains several fields, right? So you're going to look at the mystruct, you're going to see how many bytes it is. And I'm telling you here that it has several fields, X, Y, Z, C1, C2, F1, and F. And I want to know which field is stored first. How do we do that? Well, print the address of, a mystruct.x, print the address of a mystruct.y, and make a picture on paper of where each of these fields are stored inside a mystruct. And I don't think I actually say in here, but data is an array of mystructs. So I should put that in here. Yeah, it doesn't say that. But the whole reason we're messing with data is because the elements of the data array are things of type mystruct. So if you look at data bracket 0, that is a mystruct. If you look at data bracket 0.x, that's the x field of a mystruct. If you were to print its address and compare that to the address where data bracket 0 begins, you can see how many bytes from the beginning of that structure x is stored. And you can do that for y and z, c1, c2, f1, and f. And see how many bytes away each of those are from the beginning of the structure, and you can order them. And you can make a map like, first is x, and then y, and then z, and then f, and then f1, and then c1, and c2, or whatever. So figure out what the first field is. And then use the size of to figure out how big each of these fields is. Add those up, and that should be, how many bytes you actually need to store a mystruct. So I think these are ints and characters and floats or doubles, but the size of will tell you how many bytes are used. And what you'll find out is that the total number of bytes you need to store this information in a mystruct is smaller than the actual size of a mystruct. And this is analogous to what we saw when we worked with nodes. Remember, we had a structure called myNode that had an integer field and a pointer field. And the integer takes 4 bytes, the pointer takes 8, but this whole thing took 16 bytes. Because the way it was stored in memory, we had 4 bytes for the data, and we had 4 bytes that were unused, and then we had 8 bytes for the next. And so from PA1, our struct myNode allocates 16 bytes, but we only really need 12, right? A pointer for 8 and a data for 12. But there's padding in there. In the case of a struct myNode, right here, there's 4 bytes that are not used. They're just wasted. And so your goal in question 10 is, since the number of bytes needed is less than 32, spoiler alert, that's the size of a mystruct, there must be unused space. So what's the address of the first unused byte? So if this was a myNode we were asking about, I would want to know the address of this, add 4, that's the address of this unused block. That's the answer for the question. But the mystruct in this quiz is much more complex, so you need to map all of this out on paper. And I am totally fine if you want to work with other people on this, provided you're not giving each other the answer, right? Working with somebody is not, what did you get for 10? Okay, But if you want to, you know, work together to figure out where the stuff is in memory, what the memory map looks like, in a way where you're learning it on your own, right? I'm okay with that. Right, so these quizzes have point values because if I didn't put point values, nobody would do them. But I'm not, you know, doing it to test your understanding or decide if you go on to 223 or something like that. This is really, you know, exercises for you to work through and learn from. And the GDB quiz is the trickiest of the quizzes because, you know, it's got all the stuff you have to do. The other quizzes are mostly along the lines of, you know, just short answers. So I won't do as much detail on these other ones, but let's look at the next few of them. So quiz 3 is about linked lists, right? Which of the following is true about memory in linked lists? Sentinel node in a linked list, which one of these is true? A linked list compared to an array, which one of these is true? When thinking of PA1's linked list as, oh, we can't do this one. Alright, I will get rid of this question because we didn't do that PA1. As an abstract data type, which of the following routines is typically not supported by the interface to a linked list? So I'll get rid of question 4 because we didn't do that code. So I'm going to make notes to myself. All right, and let's see. So quiz 4 is due February 9th, so now we're getting further out, but we'll take a quick peek at this, and I think this is about hash tables, yeah. So which of the following is not true of a hash? Oh, it only lets you do these one at a time. Alright, so questions about hash tables. And then, yeah, and then we're out into March. So the others are for the end of the course. So take a look at those and let me know if you have questions. Well, let's pop through them anyway. Oh, cool. Tries and trees, so we're going to get into trees later on, maybe later today, and definitely next week. And then quiz 6 is heaps. And heaps are a special type of tree. And they're everybody's favorite data structure. And then more gory details on trees. So this will be much deeper in the course. Alright, so go through those, do them when you can, get them out of the way, ask questions if they come up. Alright, questions? Alright, on to trees. So trees are sort of the data structure we've been heading for through all of this. And we usually talk about binary trees, but let's start with kind of the most general notion of a tree. We have some node. So a node is, you know, typically a structure that contains some piece of data. plus other stuff. In a linked list, a node is a piece of data and a pointer to another node. In a doubly linked list, a node is a piece of data plus a pointer to the next node and a pointer to the previous node. And so in a tree, right, we have a node, and it contains pointers to 0 or more other nodes. And each of those nodes can contain pointers to other nodes. And each of those nodes might contain pointers to other nodes, or might not. And on and on and on. So there's properties of trees, and there's terminology. So let's look at some of the properties first. Well, let's do terminology. So I'm generally going to call these nodes. So node is just, you know, an element of the tree. And a node can point to, you know, 0 or more other nodes. And there's a directionality to this. So think of like a family tree, right? Except it's a family of like humans who reproduce without partners, I guess. So like tribbles. So, but it's a sort of a family tree in the sense that, you know, this is a descendant of that, this is a descendant of that, and also therefore indirectly a descendant of this node up here. And so there's a node which is, you know, sort of the starting node for all the others, and we call that the root. And when a node points to other nodes, those nodes are called the children of the node. So this would be a child of this. This would also be a child of that node. This would also be a child of that node. And so let me put in some data for these nodes. So there's a tree. So A is the root. And C is a child of A, right? Because it's pointed to by A, and so let me put arrows on here for now. So C is a child of A. We also say A is the parent of C. So any node that you're pointing to is one of your children. Any node that is pointing to you, that is your parent. Alright, a node with no children is called a leaf. And so the leaf nodes in this tree would be D, E, H, I, and J. These are all leaf nodes. And so if we draw it like this, where anything in some position points to the things that are lower than it. In other words, when we draw it like this, we're understanding C is not pointing to A is pointing to C. And so we usually draw it without arrows, and we simply understand that anything that's drawn lower on the page is being pointed to by whatever it's connected to higher on the page. And so this is actually an upside down version of you know, a natural tree. So an actual tree, the root is in the ground and the leaves are up in the air. And as the tree grows, you know, the branches bifurcate or trifurcate, and you get more branches and so on. And at some point you don't get any more branches, you just have, you know, the leaves sitting at the end. So it's modeled after, you know, a biological tree, but we draw it upside down for whatever reason. And so it turns out, somebody sent a joke in chat, but it's not a joke, right? We actually do use terminology. Like, for example, D is a grandchild of A, right? Because D's parent is B and B's parent is A. And we will sometimes talk about, you know, B and C are siblings because they have the same parent. And we can talk about aunts and uncles also. So F would be an aunt or an uncle to I, because it's a sibling of I's parent. And when we get into the really hairy algorithms on trees, something called red-black trees, the code we write will actually deal with things like grandparents and grandchildren and aunts and uncles. But most of what we do will pretty much deal with just parent and child. All right, so that's some initial terminology. Some of the properties that make this thing a tree as opposed to just a bunch of circles with arrows. So particular terminology. Every node has a parent except for the root. The root has no parent. Every other node does. And if we had another node that did not have a parent, you know, it could be, you know, some other root sitting out here like that. That's not considered a tree anymore. So we don't want that. All nodes are connected to each other. So, you know, I could have something out here like that. That's not a tree anymore. That's actually two trees. And so we'll talk about a forest being a collection of trees. So everything has to be connected to everything else. And this in particular means, you know, you can get to any node from the root. So if I want to get to this node out here from the root, what do? I come down along this branch to this node, I come down along this branch to this node, and then I follow this branch to this node, and there I am. and you can always do that. There's no loops or cycles anywhere. We would not have a case where, you know, D, for example, would point back to B. If you have a graph, that's okay, but for a tree, that's not allowed.
How would you structure the tree? Like, how would you know which side or what goes in the left one as opposed to the right one?
Oh, that depends. And that will be a critical question down the road. But we're going to hold off on that for a little bit. But depending on what you're doing with the tree and how you're organizing information with the tree, there are good answers to that. But I'm still thinking pretty abstractly at this point. All right, so if we have a tree, well, I can just keep picking on this one. So if we have a tree, we can talk about the depth of a node. And so the depth of a node is the number of steps from the root. I've said that, you know, you can get to each node from the root. So if we pick any node, we should be able to say, well, how many steps does it take to get here from the root? So the node D, how many steps do I need from A? I have to go 1, 2 steps. So this has a depth of 2. The node H has a depth of, starting from the root, 1, 2, 3. It has a depth of 3. The node B has a depth of 1. 1 step from the root. And if you draw your tree neatly, what you find is that, you know, all the things at this level are going to have a depth of 1. All the things at this level will have a depth of 2. All the things down here will have a depth of 3. So it's really, you know, sort of how deep you go down the page. By convention, the root has a depth of 0. Because how many steps do you have to travel from the root to get to the root? None. So the depth of the root is 0. So each node has a depth, and each tree has a height. And the height of a tree is just the maximum depth of all the nodes. So the depth of the deepest node. So the height of this tree would be 3. Why? Because I have nodes with a depth of 3, and that's as deep as any of the nodes get. So nodes have a depth, trees have a height. Alright, so we have nodes that basically contain pointers to other nodes, but they also contain a piece of data. And it could be, you know, an integer, could be a string, could be a more complex structure, could be a linked list, could be a hash table. But there's you know, some sort of data component to each node, and then a series of pointers to other nodes. And we're mostly going to be interested in binary trees. So a binary tree is one where each node has at most 2 children. So these are not binary trees. C has 3 children, it's not a binary tree. But if I do something like this, right, that's a perfectly fine binary tree. Each node has, you know, either 2 children, such as A, or 1 child, such as J, or no children, such as K. And since we know that at most there's 2 children, we can name the children. And so we could say, for example, I is C's left child, and J is C's right child. So this is left and right. I'm making notes as I say this so that I don't repeat myself too much next time. Alright, so every node has, you know, up to 2 children, a left child and a right child. We can also think about subtrees. And so A is the root of this entire tree. A happens to have a left child, B. We can think of B as the root of an entire tree also. If we ignore all of this stuff, we've got another binary tree whose root is B, and it has children on the left and children on the right. And this whole tree is actually just hanging to the left of this actual root A. And if we ignore everything from the root and to the left, we have another binary tree over here, whose root is C. C has 2 children, I and J. J has a child, K. This is a tree containing 4 nodes. So each node is also the root of some subtree. A smaller tree. And this is a hint to something we're going to do later on, what I call recursion, right, or what I've referred to, or hinted at. Since a tree is actually just, you know, two other trees connected to this root, we're going to be able to do things with this entire tree by doing things to this smaller tree and doing things to that smaller tree. And so trees are going to lend themselves very naturally to breaking a problem down into smaller pieces, tackling those smaller pieces, putting the solutions together. And that's going to be a lot of what we do for the next few weeks. Alright, so you're going to mostly concentrate on binary trees. And let's think about trees of integers. And let me tell you why we care about trees. With the definition that I've given you of a tree, is this a binary tree? What do you think?
No, it's just a linked list.
But is it also a binary tree? Does it have a root?
It does have a root, but it doesn't have a second node offspring to make it, binary.
But for example, B didn't have a child to the right, but we still said this was a binary tree. Well, a tree, right? And G has no child to the left, but it's still a binary tree. And if every node is the root of a subtree, technically G should be the root of a subtree. This whole thing should itself be a tree. And you're absolutely right, this is a linked list, but it's also a kind of degenerate version of a tree. Right? As long as it's connected, there's a single root, there's no cycles, every node has 0, 1, or 2 children, it's a binary tree. And by the same measure, this would also be a binary tree. But they're really just linked lists, right? It's just a node pointing to another node pointing to another node. And this is a powerful realization now that binary trees include linked lists. Everything we know about linked lists, those are really just one very particular example of a not very interesting binary tree. But technically we can look at them as a binary tree. Okay, so forget about trees for a moment. Let's just go back to linked lists. And let's make a linked list of integers. So we'll have a 10, points to a 20, points to a 30, points to a 40. Alright, there's a linked list of 7 integers. And what we've done so far, we have a sentinel node pointing to the 10. So if you want to find a 60, what do? You start from the sentinel. You look, nope, 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 bingo. I found my 60. Worst case, it's going to take you 7 tries to either find, a 70 or to find that a number you're looking for is not in the list. Now our data is sorted, and we know if we have a sorted array, we can do better than order n. If we have a sorted array, we can play high-low. We can say, let's check the number right in the middle. And if we're looking for something smaller than that number in the middle, throw away the second half of the array. Let's just check the first half. And our problem is half is large now. And we check the middle of that. And if the number that we're looking for is bigger than the middle of that smaller array, we throw away the first half of that. And now we've got a tiny little array that's 1/4 the original size. And the nature of this binary search, this high-low game, is that each time you do an operation, you cut the size of the search space in half. And so if you have 1,000 numbers in your array, after 10 comparisons, you'll have gotten down to an array containing a single element. Because you cut 1,000 in half 10 times, and you end up with something smaller than 1. And so this is why binary search is so fast. This is why high-low lets you guess a number, between 0 and 1,000 in 10 tries instead of 1,000. So if we wanted to search for the number 60 in a linked list, we can't do this. Because what we'd like to do is we'd like to start with a number right in the middle and say, is our number to the left or the right of that? But we don't have a pointer to that number in the middle. All we have is a pointer to the first thing in the list. So what are we going to do? We're going to modify our linked list. And we're going to say, instead of having something that points to the first node, let's have something that points to the middle node. So we've got our list of data. We're going to keep a pointer to the thing right in the middle of the list. We're looking for a 60. We're going to check this number as a 40. 40 is smaller. So what do we know? We can ignore everything from here to the left. And now we've got to check this list, which is much smaller. It's half the size of the original. We've got to check this for a 60. Well, all things being equal, all we have from this middle node is a pointer to the 50. And so we'd have to go through this list sequentially. So we cut the list in half with our first operation, but now we're back to an order n. What we'd really like to do is say, okay, our number is somewhere in this smaller list. Let's start with the middle. So we want a pointer to the middle of this list instead of a pointer to the beginning of it. So instead of having the 40 point to the 50, we're going to have the 40 point to the middle of the list on the right. And now we're going to search for a 60, and bingo, it's right there. And if we were searching for something smaller than 40, well, having this point to a 50 or point to a 60 doesn't do us any good. And we could point to the beginning of this list, but that's in order n. Really, if we're looking for a number and it's smaller than 40, we know it's somewhere in this list. We'd like to start at the middle of this list. And so let's have a second pointer in this node that points right to the middle of that list. And similarly, in the 60 node, we're going to have a pointer that points to the middle of the list on the right and the middle of the list on the left. And the 20 will have a pointer to the midpoint of the list on the right and the midpoint of the list on the left. And so we're going to make our linked list very funky by adding extra pointers. And instead of pointing to the next node in the list, we're going to point to the midpoint of the entire sublist on one side or the other. So what does this modified linked list look like? We've got a 40 that we originally point to. That's the only thing that we have to get a hold of this list. And the 40 has something that points to a 60 and also something that points to a 20. And the 60 has something that points to a 70 and also points back to a 50. And the 20 has a pointer to a 30 and another pointer to a 10. And this is a binary tree. So this is a linked list where instead of each node pointing to one following node, we have a pair of pointers. Something that points to the halfway point of the sublist on the right, and something that points to the halfway point of the sublist on the left. And this lets us do high-low when we want to search for something. And so this is a particular type of binary tree. Called a binary search tree, or a BST. And this is what we're going to study for the next couple of weeks. And it comes from the idea of wanting a linked list type structure where we can squeeze things in between nodes or remove nodes without having to, you know, shove everything up one way or another in an array, right? Because we have pointers to all of our data, so we don't need to relocate data to put something before or after a node. But it brings back this ability to do high-low when we want to search. And so if I want to search for the number 55, right, I started the root. 55 is not there. It's bigger than that. I can ignore all of this. And I can say, hey, if 55 is in my tree, it's somewhere in this subtree. So I check the root. 55 is smaller than 60. I can ignore all of this. If 55 is in my tree, it's in this subtree. This tree only has a root, nothing else. Is the root equal to 55? No, I'm done. 55 is not in my tree. But I didn't have to do 7 comparisons. I did 3. And so this is going to be order log n. And that's so much better than order n. Order log n means if I have a billion times more data, it's going to take me 30 times as much time. Because log of a billion is about 30, log base 2. So a billion times as many numbers in my tree, and instead of taking a microsecond, it takes me 30 microseconds. That's a really, really good performance. Log n, I would go from a microsecond to a billion microseconds. Well, how long is a billion microseconds? It's 1,000 seconds, so it's about 20 minutes. So you want to spend 30 microseconds or 20 minutes doing your search. So log n is really, really a nice performance. Alright, questions. There must be tons of questions at this point. So how would you represent a binary tree in C? What sorts of things would you do to create this structure? And you can start from a linked list and try to build from there. Let's see, how would you know where the middle of the list, root of the tree is, if you are just handed a tree? Or are we just building a tree from nothing? So if you're handed a tree, you're going to be handed the address of this root node. And the root becomes the handle of the tree. So the root is kind of like what we were doing with a sentinel node, but it's not a sentinel node. The root is actually part of the tree itself. And so if this was the data represented by a tree and I wanted to, pass it to a print routine, for example, I would pass the address of this root node.
I think maybe he's asking, what if we were just given a list of numbers? How would we decide which number should be in the middle?
When you build a tree, this will sort of answer itself. So if you're building a tree, you start with an empty tree, so the root is null. And the way that you decide where to place the nodes kind of implicitly creates the root at each step. But we need to get into the algorithms for actually constructing and manipulating trees, and we're not quite ready for that yet. But when you construct a tree, you're going to do it one node at a time. So whatever node you start with, that's going to be the root to begin with, and then the other nodes will change the tree depending on how they compare to the root. So yeah, we basically have like a next node and a previous node, except it's not next anymore. It's something in, that side of the node, but it's not the one right after it. It's the one like in the middle of the right sublist or the left sublist.
So like baby child,
Sorry, say again?
child and parent.
Yeah.
This kind of raises up a question for me.
Okay.
How would you know what the address is for the next node kind of idea?
For the what?
For the what is it, the I figure out, how would you know where the next not like the next node, but like
The next
that thing that's pointing, yeah, it's like
Oh,
how would
this.
you know where the 60 is pointing, where the 60 is in memory?
Yeah, it's a beautiful question with a beautiful answer. This is where that arrow notation is going to make such a big difference for us. So let's think about the structure for a node. So what would a node look like in a binary tree? Let's just suppose that we're storing integers, because integers are nice and easy to work with. And we're going to have a pair of pointers. One that points to the middle of the left sublist, one that points to the middle of the right sublist. So we're going to have a struct node star, and I'm going to call this left. And we're going to have a struct node star right. So each node is going to have three fields to it. A data piece, which is, the number that we're storing in the node, and then a pair of pointers, one pointing to the left, one pointing to the right. And we can think of this, if we thought of this as a list, it's pointing to the midpoint of the sublist on the right, but it's actually pointing to the root of the subtree on the right. And the left field of this node is pointing to the root of the subtree on the left. And so let's suppose we have a root. Alright, so here's the root. The address of this node will be root arrow right. So root is the address of this node. When we say root arrow right, it says dereference that pointer, find the structure that root is pointing to, and pick off the right field. Well, that's an address, and it's the address of this block. So this node right here we can refer to as root arrow right. This node right here, well, if we know the address of this node, which is root arrow right, what we want to do is dereference that get to the structure, look at the field that's called right, well, we can just say arrow right. And so this node we can refer to in C code by saying root arrow right, arrow right. And if we want to find this node, what do we have to do? We have to take the address of its parent, which is root arrow right, arrow right. That's an address in memory. If we dereference it, we will find a block of stuff corresponding to a struct node, and we want to see what the left field of that is. Well, that's just putting an arrow left after this. So this node we could get to by saying root arrow right, arrow right, arrow left. And so it'll be very, very straightforward in C to be able to refer to nodes relative to another node by using this arrow notation. And it practically writes itself once you're comfortable with it and you believe it. Because, you know, root arrow right, arrow left. And if I wanted the data field of that, it would be, you know, all of this stuff, arrow data. And that would give me, you know, the number that was stored in this node. All right, other questions? So we're a ways away from having to do this. This is going to be PA4. So this is much further down the road, but it's going to take us a few weeks to go through everything that there is to say about binary trees, everything that we're going to say about it. It's a deep subject, and it's almost the quintessential data structure. So many things that we do are variations of trees. And, you know, we can have versions of trees that relax some of these rules. For example, we might allow cycles. We might allow a node to point back to the root, for example. And then it's no longer a tree, but it's something called a graph. And a graph is a generalized version of a tree. And graphs are useful. If you've done 215, we talked about graphs. If you're in 215 now, we'll get to them towards the end of the course. But graphs are a really powerful way of representing relationships among different things. So we can represent, you know, the internet as a graph. We can represent connections among people in Facebook as a graph. And so a lot of what we do with trees, we can also do with graphs, but, you know, understanding that graphs have, for example, cycles in them. All right, well, let me just leave you with a bit of a preview. So here's our binary search tree for 7 integers. And, you know, if you're looking for a number, you start from the root and you look in either the left or the right subtree, depending on how your number compares to the root. And if your number is equal to the root, you're done, you found your number. So if I'm looking for a 20, I'll move to the left here, and bingo, there it is. If I'm looking for a 21, I'll move to the left. Compare it to 20, it's got to be to the right. I'll compare it to 30, it's got to be to the left, and there's nothing there, so 21's not found. So this is how we play high-low with a binary search tree. We're sort of guessing in the middle of each thing on the right and the left. And if I wanted to add a 21, I can do what I just did when I was searching for 21 to figure out where a 21 should go. So it should go to the left of 40, it should go to the right of 20, it should go to the left of 30, and there was nothing to the left of 30. That's how I knew 21 wasn't there. Well, if I want to add a 21, I'm going to put it right there where it belongs. Bye. Thank you.
Huh?
Thank you.
Yeah.
And so we'll talk about how to add things to, we know the basic idea of how to search for something in a binary search tree. We'll talk about how to add things to trees. We'll talk about how to build these up. And this will take us into discussions of other properties of trees, things related to what we call balance. And eventually we'll work up to talking about how to delete from a tree. Deleting from a tree is fairly tricky. And in general, the operations we do on these trees will be a lot more complex than they were for linked list, because it's a more complex structure. Not only because we have 2 pointers for each node, but we have certain relationships that need to be satisfied. So the manipulation will be more complex, but the payoff is the performance will be generally log n instead of n. And that's going to be worth the added coding headaches. All right, so we will continue with this on Monday, and we'll get deeper into binary trees throughout next week. All right, come by office hours tomorrow if you've got questions, particularly on PA2. Those are my last office hours before the due date. So, but it sounds like people are pretty much have that under control. So. Have a good one. I'll either see you in 2:15 or I will see you on Monday. All right, thanks.